resulted from a paper we published a few months ago, and the long-standing controversy over what causes topography. So, as many of you know, I've been involved in building an experimental planet for quite some time. And the talk today is sort of part of understanding how the Earth has evolved through deep time, and perhaps also how it will evolve in the future. Of course, there might be some things, going wrong with the Earth at the moment. It's probably not because God made a mistake, It's mostly humans to blame. But never mind that. So we're going to have mostly a look at what the Earth has been doing or might be doing without humans. It's probably better off, Okay. So topography, right? I mean, everybody knows what topography is, especially rock climbers, right? Now, pretty much Earth's topography is largely a product of plate tectonics. Without plate tectonics, the topography of the Earth would be pretty flat. Like other planets that don't have plate tectonics, like Venus, for example, or Mars. These planets might have had plate tectonics at some point in their history. That is still debated. Okay, so we're going to focus on Earth for the moment being, because we're interested in topography for a whole bunch of reasons. So on human time scales, of course, topography drives ecosystems, human settlements, groundwater, sea level. We are particularly interested in how topography modulates coastline migration through time, especially in the context of sea level change. And of course, sea level has changed enormously through geological time. So topography, everybody's familiar with images like this one from the Swiss Alps, where we see spectacularly folded up mountains that were, of course, caused by the collision between sort of the African plate and particularly Italy sitting at its northern extent, ramming into the southern edge of Eurasia. Right? So this is what's called tectonic topography, caused by plate collision and deformation. But we have other types of topography, like the Blue Mountains, for example. And this is a view from the Three Sisters, and I'm sure many of you have, towards the Three Sisters, I mean. So many of you have probably been there and taken a photo like this. So you notice the difference to the topography in the Swiss Alps immediately, right? These layers are not wildly folded. They're all nicely flat lined. Right? And so somehow these mountains have come up without collision and without folding. Right? I mean, it looks like they've just sort of gently risen, perhaps. Right? And of course, this brings us to the question, so what drives this type of topography? Right? So we look at the Eastern Australian highlands from a bird's eye perspective. Right? And so the entire eastern margin of Australia is in fact uplifted. Right? And so the question is, well, how did these eastern highlands and other similar highlands on Earth form? There's also highlands in Brazil, for example, that look not dissimilar to the eastern highlands of Australia. And so this observation brings us to dynamic topography. So dynamic topography is topography not driven by plate tectonic processes at the surface, but it's driven by mantle convection. So we have, of course, the Earth's mantle, the bit of the Earth between the surface plates and the core. If you could go down, like in the famous movie The Core, and take a hammer and check out the material down here, and disregarding the enormous temperatures and pressures that exist down there for the moment being, and it will sort of look like a rock to you, right? And just like you can wander about on a glacier and it looks pretty solid, but what the glacier and the Earth's mantle have in common, over long time periods, they can actually flow like a fluid. Right? And so that the mantle's viscosity is pretty high, right? But it does flow like a fluid over geological time. And so we have upwellings and downwellings, and these upwellings and downwellings are coupled to what the plates are doing at the surface. Because the plates are moving around, they're converging, like around the Pacific Ring of Fire, and we get subducted slabs descending into the mantle where all the oceanic plates are recycled back into the mantle, and they will ultimately fall all the way to the core mantle boundary. And since we have to preserve the mass in the mantle for all the stuff that's going down, well, something's got to come up. And so we get very large scale upwellings in the mantle, thousands and thousands of kilometers in diameter. So these are sort of passive upwellings. But we also have what's called active upwellings. These are individual cylindrical upwellings that are called plumes, and they're caused by really Taylor instabilities at the core mantle boundary, and they're much more vigorous than the large-scale upwellings. And so that gives us an idea of the ups and downs in the mantle, and of course the coupling between the convecting mantle and the surface plates in the Z direction causes the topography to undulate at the surface. Now, one of the reasons, practical reasons, why humans are interested in understanding, the physical properties of the mantle, its viscosity, and how it responds to changes in mass at the surface, is in fact related to ice sheet growth or melting. So this is a figure from a paper by Conrad from 2013. And if you just start here on the upper left, so we have an ice sheet on a continent, and so if we say melt this ice sheet partly or entirely, then what's going to happen is we are going to take mass away from here, so we are going to unload this part of the continent, so it's going to go up. So this is going to be our new ground surface here, that's what used to be down here. Right? But at the same time, we're also going to raise sea level. Right? And so previously, and this sea level is not actually, you notice right away that this is not a straight line. And the reason for this is gravity. So because we have a large chunk of mass here, much more than say over here, this excess mass actually attracts the water, and so sea level will be gently raised towards this giant mass. So if we melt the ice, so not only will the land go up and the sea level will go up as well, but the shape of the surface will change. So because there's going to be much less mass here than before, the new surface is actually going to go down, say, schematically, right? And so it's quite sort of an intricate balance. And so while you melt the ice, you actually have to look at any individual location to understand what's going to happen to relative sea level in these places. So it's not the case that you just melt the ice and relative sea level goes up the same way everywhere. Right? And so in order to predict this kind of behavior properly, you actually need a very detailed understanding of the viscosity of the upper mantle and how the surface is coupled to the mantle. So that's a practical aspect of understanding these sorts of processes. Right? Now, the problem with figuring out, what the contribution of the mantle to the surface topography is that the segment is much smaller compared to what we call isostatic or tectonic topography, the topography that's caused by collisions of tectonic plates, like the Alps and the Tibetan Plateau. So that topography is quite impressive, right? And dynamic topography. So there's an image here of non-isostatic topography plus isostatic topography, and what's called residual topography here is the topography that we cannot explain by tectonic and isostatic topography. Right? And so, but how to create this kind of map is actually very controversial. Right? And this is because at the surface, so we have the continental crust, but underneath the crust there's something called the lithosphere. So essentially the uppermost part of the conducting mantle that we looked at before, it sticks to the plates from below, and the way the temperature pressure gradient works out, there's a large chunk of the mantle that essentially gets sort of frozen, if you like, that sticks to the plate from below and travels with the crust. And we cannot sample this mantle lithosphere very readily. I mean, there's every now and then we get volcanic rocks that carry little messengers from the lithospheric mantle to the surface. Right? But we don't know very well what the physical properties of this mantle are. Right? And so that makes it an uncertain game to conclude. So what sort of topography we cannot explain by isostatic balancing, because in order to know how the continental crust and lithosphere should isostatically balance, we need to know its thickness and its density, but it turns out we don't know that very well. So the disputes on what the magnitude of dynamic topography in fact is as a function of wavelength goes back at least 2 decades at this point. There are some papers published 20 years ago based on computer simulations, and so this is a place in this is a map of Southeast Asia here. In this paper here by Lithgow, Bertoloni, and Garnes, they concluded that parts of Southeast Asia were drawn down in places by a kilometer or more. And then there's a group at the University of Cambridge led by Nicky White, and he said, no, this is all complete nonsense. And if you look at the observations, it looks like these variations are only a few hundred meters, not a kilometer or more. And so this debate has continued until recently. Perhaps it's still continuing, hopefully not. And so here are some figures that compare geodynamic models from 4 different authors that all try to predict what the present-day dynamic topography contribution would be to surface topography. And so where the red bits are denote uplift, and the blue bits depressions. And so you see right away what all these models have in common. They seem to agree that there is some kind of an upwelling underneath Africa here, or parts of Africa and the Atlantic, and there is another one under the Pacific. But what exactly the wavelength and shapes and amplitudes of these upwellings are varies quite a lot. Right? And so these maps are all made using the same scale. You see some are quite pale, right? And others are quite vivid, meaning that some models predict, very large contributions here, and others not. And so mostly this reflects differences in assumptions that are made about mantle viscosity and its change in depth, and the way these models are set up as well. And so then we can compare this with a collection of maps that are called global residual topography. And so here now we're not looking at the problem using the geodynamic forward modeling simulation, but looking just at observations. But the observations are quite ambiguous is the problem. And first of all, you can see that the residual topography is the topography we seemingly cannot explain with isostasy. We take away all the contributions from mountain chains that are assumed to have a root sticking into the mantle. And this is like making the topography flat at the surface, and then having the tectonic topography and its isostatic contributions, and having a look at which undulations you cannot explain this way. Right? And you see, so not only do these maps also look different from each other, they don't look like the previous 4 maps. Right? So there's a disconnect here. Right? So we're going to have a look at this disconnect here today. Right? And so there have been all sorts of efforts to reproduce this apparent smaller amplitude and also shorter wavelengths of this residual topography. And one way to do this is so these plots here from an old paper from 2000 that show the fit of residual topography of model topography, either to the observed geoid or the observed topography. Now the geoid is a surface of equal gravitational potential that surrounds the Earth. Right? And so these are 2 views of the Earth's geoid that are vertically exaggerated. And so the Earth's geoid looks like a potato, because the Earth is rotating, and the very first approximation, the Earth's geoid looks like an oblate spheroid, a spheroid that has an equatorial bulge. Right? But because of the irregular distribution of mass in the interior of the Earth, if you're cruising along at an equipotential surface, and the sea surface is such an equipotential surface, right? Because of course water can flow, and it will naturally form an equipotential surface. Once you get rid of waves and currents, right, then you can actually use the surface of the oceans and of rivers as well, and canals within the continents. Because what these bodies of water have in common, they all follow an equipotential surface. And you can map these things using satellite altimetry these days. Satellites that measure the distance between themselves and the water surface using radar. And as long as you can check their position accurately, you can figure out what the geoid looks like. So it turns out that you plot residual topography against the geoid, you actually get a good match. But the geoid is actually very strongly dependent on very deep mass anomalies. So the geoid, the gravitational field of the Earth, it doesn't just see very shallow density anomalies, it actually sees deep into the Earth. Right? If you have big blobs of mantle material that are either denser or less dense, sitting somewhere 1,000 or 1,500 kilometers below the surface, you can actually see those things in the gravity fields, right? And so this is actually the first sort of giveaway that the residual topography, even though we are looking at the geoid here at the moment, probably has something to do with a deep mantle structure, right? But then if we just look at the surface topography or the residual topography itself, it's all over the place, and we cannot seem to make any sense of this, right? Okay, so now the same group of Cambridge that I mentioned before is led by a guy called Nicky White. They went ahead and compiled a lot of observations all around the world. So this is a bit of a funny projection here. But so all these little dots here are places where they've tried to figure out what the so-called residual topography is, the surface topography that you cannot explain using pure isostatic balancing. And so, but in order to do this isostatic balancing, first of all, you need to know what the crustal thickness is, because the thickness of the crust determines how much the surface sticks out in a way. Because the thicker you make the crust, well, the more the surface will stick out, right? So for example, the Himalayas, well, they stick out a lot at the surface. They also have a deep roots in the mantle, and they have fairly thick crust, right? So these are all places where geophysicists have measured the thickness of the crust, usually using seismic observations, and they've also measured the thickness of the sediments that are sitting on top of the crust, if there are sediments, which of course in the oceans there are sediments everywhere virtually. And okay, and so they have they're focused on the ocean, because I've mentioned before that under the continents there's quite a bit of controversy over what the continental lithosphere, you know, the part of the mantle that sticks to the continents from below, what its density and thickness actually is, especially its density. And the reason for this is that the parts of the continents are, of course, billions of years old. If you look at Western Australia, you know, it's as old as 3.5 billion years. And so the continents have undergone many, many periods of melting and residual material being left behind underneath these continents. So the composition of the stuff underneath the continents differs a lot depending on their history. But the oceans are much simpler. The oceans are much younger. The oldest ocean crust on Earth is about 180 million years old, which is nothing, and considering that the Earth is 4.5 billion years old. And this, of course, the reason for this is that plate tectonics recycles this material continuously. Right? And the oceanic lithosphere is much simpler. It has pretty much the same composition and density everywhere. So there the problem gets simplified. As long as you know the cluster thickness and the sediment thickness, you can figure out what the surface elevation should be. And if the surface elevation is different from what it should be based on that, then you say, okay, you turn that into what's called residual topography. Everybody follows that so far, yes? Okay, and so here's a view of what they're doing. So this is 3 different seismic sections that show layered sediments on top of the ocean floor, and so the snapshots of how you then figure out how thick the sediments are and how thick the crust is, and how you play this game. And so here, So this is how it works. So this is the original interpreted column. You've got water, you've got some sediments, you've got the crust, and then you've got this spherical mantle. The reason is that scientists and industry alike are much more interested in the continental margins than the ocean crust. And so they've gone out and they've shot seismic lines across these resource-rich continental margins of South America and Africa. And every now and then, they have, because they're trying to capture the transition between the continental crust and the ocean crust, which is shown by the dashed line here. And because we are trying to focus, or they were trying to focus on the ocean crust here, because it's much simpler in structure than the continental crust. And so these the companies and scientists who have shot these seismic lines, they're mostly interested in this area in here, and then they go out a little bit further and get some observations on the ocean crust before they turn back. So that's why you have these clusters of points here, just outboard of this dashed line, which is the boundary between continental and oceanic crust. And so they went ahead and mapped the residual topography along a profile here and here. And the result is shown by just disregard this continuous line for now. It's shown by these little symbols and error bars. Right? So this is for South America, this is for Africa. And what you see is there seem to be lots of ups and downs, and the scales these are wavelengths of, so that's 1,000 kilometers here. So the wavelengths are something between 2,000 kilometers. And so these are undulations that they cannot explain using isostatic topography. So they say, well, this reflects something that's going on underneath. Right? And but of course, whether or not these same processes occur in the open ocean basin here, who knows? Because there's very little data. Right? Now. If we so this is our own plot of those data points that they've made available with their paper in Nature Geoscience from 2016. So Hogarth was one of Nicky White's PhD students at Cambridge. And so when we go and contour up their data and we plot residual topography against dynamic topography that comes out of a modern geodynamic model, right? We actually find a pretty good correlation, and we look at these data at face value, and it looks like the coastlines are a little bit hard to see here. There's South America, North America, there's Australia, Eurasia, and Africa. And despite the very uneven distribution of these data points, so what you see is that you get two large-scale upwellings and two large-scale downwellings, right? Which is what we expect, because these places are all deeper than they ought to be, because they're aligned with subduction zones. And so the subduction has been going on for a long time. The old oceanic crust is being recycled back into the mantle. And these places here are the return flow, the stuff that comes up in response to all this material going down. So we say this all makes perfect sense, right? And it turns out that the amplitude of this long wavelength topography is about is up to 1 kilometer, 1 kilometer up or down. And this is consistent with with geodynamic models that have been carefully calibrated against what we know about mantle viscosity, etc. And so this seems like this is all fine, and this whole problem has been solved, right? But however, so these guys published this paper in Nature Geoscience, and they didn't come to this conclusion at all. And so the conclusion that they came to instead is that there are no large-scale upwellings and downwellings in the Earth at all, right? And in fact they came to the conclusion that the large-scale upwellings and downwellings, and they're sort of extracted out of their residual topography model here. They're very, very faint, right? So they are perhaps just 100 or 200 meters in amplitude, and the only high amplitude features in their residual topography are all these little ups and downs that we have looked at before along the coast of Africa and South America, right? And so their view of the Earth is this mottled thing where there's lots of little ups and downs. And so, of course, they can, and so the individual, but because the individual measurements are not uniform enough I guess, to favor one or other solution, you can account for all the individual observations that you have by ascribing all the anomalous topography to relatively small scale ups and downs, and say there's nothing happening at long wavelengths at all, and the deep mantle is not doing anything, making no contribution to the surface topography. Now, and so we went back and had a look at this, so in fact our collaborator Ting Yang, who's a postdoc at the University of Melbourne, we have been working with that group for a long time, and so he ran his models and confirmed, and his models seem to confirm that there's long wavelength topography with amplitudes up to a kilometer, whereas these guys came to the conclusion that there's hardly any, right? And that you can explain all these observations, with regional smaller wavelength ups and downs. And so the question is, so this is a sort of this could be turned into an inverse problem, but we weren't yet smart enough to actually figure out how to solve this as a pure inverse problem, right? And so we did something for you guys to consider. And so what we did instead is so what the Cambridge group did, and what we did as well. So in order to fill the gaps, between the irregular observation points here, what people do is they use spherical harmonic expansion. Right? So. And we'll have a look in a minute at what that is, to turn this into a continuous surface. And so it turns out the tricky bit is in exactly how you do that, how you drive the spherical harmonic expansion. And so spherical harmonic expansions are a little bit like Fourier transforms on a sphere. And so it decomposes these signals into their different wavelengths and tries to figure out what the contribution of the different wavelengths to your observations are. Right? And but on a sphere, this is not done with sines and cosines, but it's actually there's lots of sines and cosines in here, as you can see right away. But the way they're combined here, they actually form Laplace spherical harmonics. But you can think of them as Fourier transforms on a sphere. Right? So this is just a little step back here to go to Fourier, right? To whom this all goes back. That you should be able to approximate data with such periodic functions. Right? And so he had this idea that any periodic function at all could be represented as a weighted sum of sines and cosines. Right? And so the interesting thing is that nobody believed at the time that he was right. So Lagrange, Laplace, Poisson, and they said, no, this must be completely wrong. Right? And it was not translated into English until like 70 years later. Right? And so of course now we all take this for granted, but this was long and thorny roads to actually get accepted. Right? And so this is a very old figure here, the temperature of a heated iron ring that was thrust into a fire, and as if you imagine unfolding the iron ring, it had a temperature distribution like this. It had this step function in the middle, and what he demonstrated at the time is that if you sum up the right set of sines and cosines with the right amplitudes and the right phase legs, then voila. You can reproduce something like that, and you just have to add a few more short wavelength ones until you do a better job approximating this thing. And so he ultimately showed that you can reproduce any function this way. Right? And so if you transplant this to a sphere, right? So then you get these Laplace spherical harmonics. Right? And you can think of them as combinations of so-called zonal and sectoral functions, and then if you combine them, you get tessera. Right? You get this combination of the squares, and so if you now imagine just akin to fitting sines and cosines to Fourier's iron ring, if you now combine lots of these functions with different frequencies and different amplitudes and different phase shifts, then you're going to be able to represent any kind of data on the sphere. So it's totally analogous to Fourier's to Fourier series, right? And so these just some more pictures about spherical harmonics. So you have the sectoral degrees m and the zonal orders n, and you can combine m and n in different ways. And so you get the idea. Then tesseract patterns emerge, and if you combine lots of these together, you end up being able to reproduce actual data on the surface of the sphere. And so this is actually just another image documenting the same thing. Okay, so now we want to fit these spherical harmonics to our data. And so if we have a series of observations S, and so they would be like our residual topography observations around the world, and we want to fit them with spherical harmonics up to a certain degree n. And the degree n is always given with respect to the circumference of the Earth. So the circumference of the Earth is 40,000 kilometers. So degree 1 is 40,000 kilometers, whereas degree 2 is 40,000 divided by 2. So it will be 20,000 kilometers, and degree 10 will be 4,000 kilometers wavelength, right? So that's the way this works, right? And so you can write this equation essentially as S equals A times M, where S is your area of observations, and M are your spherical harmonic, is your set of spherical harmonics with different combinations of M and N's, and A is a matrix that scales these guys. Right? So A is a matrix that will scale the amplitudes of all these different spherical harmonics that are necessary to match your data. But and you can already see where it's going, where the problem is. If your data are very irregularly distributed, right, then there's some ambiguity, then there's some difficulty in inverting this matrix. And so you can turn this thing around and from this to this, and you can then try to solve this for the right A. And so the problem is in making this stable. So in order to make this stable, you need two factors that are called damping factors. And they are λ1 and λ2 in this equation. And so the first one, it's a positive damping factor. It forces the spherical harmonics that do not seem to contribute significantly to your fit. It forces them towards 0. Right? And while the second damping factor suppresses the spatial gradient of the function. And so it turns out the answer that you get out of fitting spherical harmonics to very irregularly distributed data depends very much on which values you plug in here. And so here's this is the second paper that those Cambridge guys published after the first one in Nature Geoscience, because they got some flack for the first one, you know. And then they wrote a second paper that was supposed to show that they're definitely right. And in fact, that entire paper doesn't mention anywhere the word damping factor and what damping factor they use. So that's a black box in their world. But they say, oh yeah, they do Monte Carlo cross correlations, and they divide up the observations into a training set and the validation set, and they divide them up different ways, and they fit their spherical harmonics, you know, to subsets of the data, and so what these plots show. So these are the spherical harmonics, right? So remember, 1 is 40,000 kilometers. Degree 10 would be equivalent to a 4,000 kilometer wavelength, or objects that are individual objects that are 2,000 kilometers in size, you know, ups or downs, right, etc. Right? And they go to degree 30 here, and they say, and so this is their chi-square misfit, and the fit error, of course, so as you include higher and higher degrees in your spherical harmonics, so you start with the really simple model, right, that only has the very broad ups and downs, and then as you include finer scale detail up to degree 30, your fit to the observations actually decreases with increasing degree, and that mainly has to do with the data being so unevenly distributed, and it seems counterintuitive, right? Because you think the model should get better and better as you include high degrees, but it doesn't. And so the problem with what they were doing is, because, as I mentioned before, the data that they have, they're curling around the continents mostly, and the oceans are very sparse, right? And so their solution is very strongly driven by what they see along the edges of the continents, where they see all these ups and downs with wavelengths of 1,000, 2,000 kilometers, and they cannot actually resolve whatever large-scale features that there might be, right? And they don't talk very much about the damping factors that they use, right? And so essentially, it's the old problem of these are your data points, and how do you connect the dots, right? You can look at it this way. If you're an engineer and you look at these points, you say, this is an electronic board, right? Clearly, and you can connect them up like this. But you're an artist, or a creative person. You say, no, it's a cat, and so that's the potential trap here. And so the Cambridge group went down the way of the cat, Yeah. So choosing the appropriate damping factor is the old optimization problem, right? So if these are your samples, yes, of course you can fit the samples. So this is essentially what they did, right? So they have these sorts of samples, and they end up fitting them with something that looks like that, and it looks just fine, right? And so these little undulations correspond to all the data along the coast of Africa and South America, right? Okay, so that's and so it turns out, but it turns out that they essentially try to use the argument that they have all these little undulations along the coasts of these continents. Means that the ocean basins all look like that. They're full of little ups and downs, right? That's essentially their premise, right? And they've deliberately driven their spherical harmonic fitting in this direction, right? But of course, you can have these little ups and downs, and they can be sitting on top of a large wavelength undulation, right? And the two things are not mutually exclusive, right? And the issue is how you tease this out of the data, right? And so what we ended up doing is we did some synthetic tests, right? And so this is very much akin to what Robert and Daniel are doing with the Badlands model. So you create a synthetic model and have a look whether you can actually resolve it with what you're doing, right? So that's exactly what we did in this paper. And so we create a synthetic topography of the Earth that is generated from spherical harmonics up to degree 40 in the scale a certain way, right? And they're randomly generated spherical harmonic coefficients, right? And how the amplitudes vary, we make up rules how this works, right? And so then we make our synthetic world, right? And it might look like this, right? So these are ups and these are downs, and we can then say, and this goes up to degree 40, right? So this would be down to wavelengths of 1,000 kilometers. And so then we can extract out of this just the degrees 1 to 3, the very longest wavelength components, right? And we have a look at what the model does. And so we have lots of small, short wavelength undulations, but we also have a large scale topography underlying this thing, right? That has a minimum that has a low at 870 meters and a high at 1,600 meters, something, right? Okay, and so then we go then we go and try to retrieve this thing, right? And say, okay, so now what we do is we just sample this grid using the exact same distribution of samples that the Cambridge group has come up with, because we have all those locations. The data set is publicly available, right? And so we sample the synthetic topography and have a look whether we can retrieve what it takes to retrieve what we put in. Right? And of course, and we look at this in the context of these damping factors. Right? And let's not go through, and we have a look at how errors change as a function of maximum degree and number of parameters. Let's just start. The derivations, it actually decreases with an increasing degree, but only to about degree 5. And once you go beyond degree 5, it turns out the data points are actually too sparse to be sure that the fit to the global topography is actually increasing or getting better. And so the fit is very sensitive to the damping factor for expansions larger than degree 5. And the appropriate damping factor decreases with an increasing degree. And so in other words, if you put more, the more detail you put into your model, right, the higher the degrees that you expand your spherical expansion into, the more conservative do you need with your damping factors. Right? Because if you do that and damp the model too much, then you end up losing all the long wavelength topography, which is precisely the mistake that the Cambridge group made. Right? And so we look at that by looking at the model roughness. So the roughness of the surface, right, is obviously it's large, but when the model has large short wavelength perturbations and vice versa, right? And the roughness increases with a decrease of the damping factor, right? And so we're going to, and so let's not actually look so much at the variance difference. And so then we are going to look at some plots. So here's our synthetic topography, right? And so then we sample it and look at what comes out if we only use degrees 1 to 3, or we we go up to we initially okay. So what it is, we fit spherical harmonics only up to degree 5 here, and up to degree 15 here, and up to degree 30 here. So we put more and more short wavelength information in it. But then we go and extract from the solution only the very long wavelength features. We then throw all the short wavelength information away, and we only look at the long wavelengths, degrees 1 to 3. Right? Because we want to see, depending on how we do this, can we retrieve the long wavelength amplitudes that we put into our synthetic model, which looks like this, right? Only looking at degrees 1 to 3. Right? And so it turns out we can do it. We can pretty much retrieve what it looks like, but only if we pick the right damping factors. Right? So what's shown here, this is actually so the roughness, the roughness of our model, it goes down as we increase the damping factor. As the more we damp it, the smoother it becomes, obviously. Right? Let's disregard the red curve. Right? Let's only look at the black curve. And so what this is here, this is the roughness of the model. Right? So going from 0 to 1. And what's shown here is the fitting error. So the error of our synthetic model as it's fitted to the data. Right? And so as the roughness, so that there's a sort of an inflection point, right? And so it turns out that you need to use this inflection point to fit your damping factor, right? So and that's the key to making this work. Now you can sort of see that there's probably a wonderful formal inverse problem in here, but we didn't have the time and patience to derive that. That's for somebody else, to do. And so this is our synthetic topography, and if we do it the wrong way, then that's what we get out, right? And clearly doesn't work very well, right? And so the bottom line of it all is, right? So if we use the data that the Cambridge group has made available, right, and choose sensible damping factors for the spherical harmonic fitting, right, then we actually retrieve, unlike the results in their Nature paper, we actually retrieve the large amplitude, long wavelength topography. So you see the large areas that are red here, and they're about colored up to +1 and -1 kilometer. So that's a very large scale expression of convection of the Earth's mantle. Right? These are all the places where stuff has been going down for 200 million years at least, if not longer, and these are the areas where stuff has been coming up, pushing the surface up, and here the surface is being pulled down. Right? And so that's sort of the first order expression of how the mantle interacts with the surface of the Earth, and it's actually in the data, but only if you read them the right way. And I think, I think we can probably pretty much stop there. And so if we were to invert the data the way the Cambridge group has done it, then we get this kind of thing out, right? Then we get some pale solution. It doesn't correspond at all to the signal that's actually in the data, right? Which should look more like this. Right? And so this was a paper that was published in Geophysical Research Letters. So it was a collaboration between Neva and Uni and myself and our long-term collaborator at Caltech, Mike Gurners. And so I think I've already mentioned most of these conclusions. So dynamic topography is an important thing for us to understand for a number of reasons. Right? And only if we understand what we're doing with the spherical harmonic expansion can we read these data properly. Otherwise we overfit short wavelengths and lose the long wavelengths. And somebody very smart in the room could figure out how to do this formally as an inverse problem. Thanks, guys.
Did you email them and ask them for the damping factors?
No, we didn't. But we could figure out what they've done, essentially, to reproduce what they've done. Yeah.
And that was the crux of it all.
Yes, that was the crux. At some point, my Louis Moresi, who's Ting Yang's postdoc supervisor at Melbourne Uni, he wrote me this email and said, geez, we're going to publish this paper, and it's going to mean the Cambridge guys don't know what they're doing. Can we do that?
They're the best papers.
Yeah, they're the best papers. Yeah, exactly.
Okay, so Sally's not here, but I'm going to pretend I'm Sally.
Yeah, right.
And Sally, obviously, if you'd only used Bayesian methodology to begin with, you guys would have done much better.
Yes, of course. That's why I'm saying. I'm sure there's people in the room who can figure out how to do this much better.
So I want to take a first sort of stab at that and try to translate what's going on into more Bayesian methodology. So you guys are trying to infer a function on the sphere, and it sounds like this damping factor you're arguing over corresponds to a prior on how smooth that function should be.
Yes.
And in particular, it's because you don't seem to have a good hyperprior on what that damping factor should be that you can't get a handle on this. There must be, are there discussions from theory, for example, about how big, about the proper length scale? There must be some information from theory about the proper length scale for these mantle convection features.
But this is the problem, right? Because I started out showing you these alternative forward mantle convection models. It's still our knowledge of the structure of the deep Earth, right, is still quite uncertain, right? Because we cannot sample it directly. We mostly have knowledge from seismology and from high pressure temperature laboratory experiments where we can subject rock samples, to mantle-like conditions and have a look what happens, And of course that happens, at very, very small scales,
So,
and then, and so still there is a lot of uncertainty around, like these length scales that you're talking about, whether the mantle ultimately looks like a plum pudding. This analogy has been used, but there's lots of pockets of material that are kind of left over that are a little bit different from the surrounding mantle, or whether it looks much smoother. It's like anybody's guess. Recently there were papers published that, for example, that suggest that there's a lot of water that accumulates in the mid-mantle, because the upper mantle is much less viscous than the lower mantle. So there's a phase transition that happens at around 660 kilometers depth, and then the mantle becomes much more viscous. Right? And so these subducting slabs are going down because they carry water in them, in the crust and in the sediments, and some of it makes it into the mid-mantle, and there's apparently this layer of distributed water, that sits down there at this level and doesn't really make it down, and that it introduces geochemical anomalies, and so there's all sorts of weird things going on in math. So the conclusion is that there's no clear. And this is how the controversy started, right? The geodynamic modelists would claim that the situation is not actually as bad as I'm making it out, because you have different observations to ground truth model. The geoid is a good one, because the geoid, as I mentioned, is sensitive to the deep earth structure. Right? And so they run their models and they think, well, they do have a handle on what's happening. But then the observationalist was going to say, now you're full of shit. You don't know what you're doing. Your models are so constrained. And the way we look at our observations, we get a different answer. So the models must be wrong. Right? And so this is how the controversy started, right? Because the observations are so sparse that the right solution doesn't jump out of the observations.
So you have no prior expectation for what the length scale of the mantle convection stuff could be. You also have no prior expectation for how big, for the amplitude of those short wavelength observations as well. So
well, the short wavelength observations are probably a little bit better known, right?